Good morning all. Today we will continue our class on analog electronics, and let me just briefly introduce the syllabus. So, the syllabus includes bipolar junction transistor, field effect transistor, and for bipolar and field effect transistor MOSFET, for both of them we will be learning the biasing technique and small signal model and single stage amplifier. So, after the single stage amplifier, we will get into current mirrors, cascade amplifiers, oscillators, and after that we will cover feedback amplifier. There are 4 different topologies of feedback, we will cover that. Next we will cover output stage and power amplifiers, and after that we will cover differential and multi-stage amplifier. So, this is broadly our syllabus, and we will follow Cedra & Smith Microelectronic Circuits, Oxford University Press, 6th edition. So, for this book all the reading materials, pictures that in this tutorial I have taken from Cedra & Smith. So, let us start our class today. So, this first class is all about signals and amplifier. So, if we look around our surroundings, we will be seeing that all the natural signals, they are generally in analog in nature, right. So, to do or process those signals to get some meaningful measurement, there are several steps. So, generally after signals we may need some sensors or transducers. So, the job of this sensor or transducer is to convert the non-electrical signal to electrical signal. So, whatever the physical signal we may have, this will excite this transducer and we will get the electrical signal. The moment we will get electrical signal, it is easy to process by electronic circuit. So, all the processing will be done in this signal conditioning, and you can think of different signal conditioning, right, like amplification, filtering. Filtering may include low pass, high pass or band pass depending on our applications. It may include isolation. So, several all of this conditioning will be put in this block. After that, the necessary signal processing, okay, to process the data in some usable format and then put it as an output device. So, it can be display, it can be storage, and for recording or for keeping the data for future analysis. So, this is broadly our signal chain. Now, let us start from the signal source. So, when we talk about the signal source, we learn about voltage source or current source. So, if we have a voltage source, so you can say that this is a Thevenin equivalent form, and if we talk about the equivalent current source, you can say that this is an Norton form, right. So, that these two terms you already know. Now, this voltage source VST and its Norton equivalent, if they are equivalent, then this equation is satisfied. VST is equal to RS IST. Now, let me ask you a question. If I have a voltage source and I have a internal resistance RS, what should be the value of internal resistance RS so that it can serve as an ideal voltage source? Can you tell me what should be the ideal value of this internal resistance RS for a voltage source? Any guess? RS is equal to RL. If RS is equal to RL, what will happen? What is my aim? To get the Vs to the a voltage source, this internal voltage, it should come over here, right. This is my aim, and if there is any circuit, some current will flow, right. So, what is this voltage here or this V0? This V0 should be equal to Vs minus Is Rs, right, and to make this equal to Vs, what should be my condition? Is Rs is equal to 0. So, if some current is flowing, what should be this value? Ideal value 0. So, you think again, suppose you have a battery, right. So, battery, there is some chemical component is there, right, and it is generating some voltage. So, the internal resistance due to those electrical resistance, ideally that should be as close as to 0. So, that the output voltage is this source, it should deliver all of its voltage to the load irrespective of the load. This will only happen, and if you are saying that if Rs is equal to RL, if Rs is equal to RL, then what will happen? This will behave like a potential divider. Have you heard this term? Resistive divider. So, what will be this voltage? Suppose this is RL, this is Rs, and they are same, then it will be output voltage V0 is equal to, suppose this is VDD, VDD into RL by Rs plus RL, and if they are same, it will become clear. So, that is for maximum power transfer theorem, that load resistance should be equivalent to source resistance, but here our objective is not to deliver the maximum power, our objective is to deliver the same voltage, right, it is a voltage source. So, the first condition is that ideally it should be equal to 0, right, but if it is not ideal, then we should have to maintain a ratio, right. So, this ratio is will be like this. Okay. So, in reality I may not have a 0 resistance source. So, in that condition, these two resistance, the relative, they should be related such a way that this Rs is much smaller than the RL. Okay. How much smaller? That depends on our output voltage requirement. There is a accuracy band will be there defined there. From that error band we will define this Rs, but in general you can tell that for a voltage source the internal resistance should be ideally as less as possible, and this value should be 0. Clear? Now, when we come to the current source, the things are totally opposite, right. Now, suppose I have this and I want, now my requirement is different. Now, I want all of this current to flow through RL, okay, as if this current is 0. Now, what should be Rs so that this current is 0? Ideally infinite resistance, right. Clear? So, please understand this concept very well, because this will be used later. Okay. So, for a voltage source, my internal resistance should be as low as possible, and for a current source, my internal resistance, as it is coming in parallel, and parallel if there are two resistance, current will try to flow towards the lower resistive path, right. So, here this RL, it should be much less than Rs. Now, let us proceed about different type of signals. So, if you have a sinusoidal signal or any periodic signal, so can you tell me, if we do the frequency spectrum or Fourier series analysis, what we can tell? This Fourier series analysis, it tells that any periodic signal we can represent as a infinite sum of sinusoids in the frequency domain, right. So, we can take a example of a symmetric square wave, whose this symmetric square wave can be expressed like a sum of some sine wave and their odd harmonics, and we will be having some amplitude. So, if we plot that this square wave, if you want to make it, this is a time domain response and its equivalent frequency domain response will be coming like this. Okay. So, this is the main waveform, this omega 0 is termed as the fundamental frequency. Okay. And you can see that all other frequencies, they are discrete component, discrete frequencies component. So, it can go up to infinite frequency or the frequency range that we require for our operation, clear. So, this is the frequency spectrum of a time domain signal. So, whenever we talk about the frequency spectrum, we generally have a amplitude response and a phase response. About phase response I will discuss later. So, similar to a periodic waveform, we can also have an aperiodic waveform. Okay. For aperiodic waveform, generally we use Fourier transform, and in previous case the frequency domain response was discrete and now it is a continuous in frequency domain. So, these two frequencies, this Fourier series and transform, this helps us to convert any time domain signal to frequency domain signal, and that is several times it is used. Now, let us quickly discuss about the different type of analog and digital signals. So, analog signals are generally all the physical signals that is available. For example, you think about temperature, pressure, voltage, flow, whatever we can see surrounding environment, natural signals, and all of these natural signals, if you think about their quality, it is continuous in amplitude. So, that we call an analog signal. Okay. We can have all the ranges of values. Now, in digital, generally we in the PC or microprocessor, this computer or microprocessor, they can use digital or discrete signals. Okay. For example, binary signals, how many levels are there? 0 and 1, right. So, if you see this signal, this is an example of any arbitrary digital signal. So, this plus 5 volt or VDD, we will call this level as level 1. Okay. So, this is my level 1, this is my level 0, this is my level 1, this is my level 1, this is my level 0, this is my level 1, this is my level 0. So, these are my logic levels. Now, here you see you have all the voltage from this level to this level continuous, but up to this level to this level I am having only two discrete levels. So, this signal is digital in nature. Okay. If it is binary, I have two levels. Okay. Similarly, you can have quad, you can have octal. Okay. So, different levels you can have, but in between the value is discrete. Clear? I hope this is clear. So, this is example of analog and digital signals. Now, to convert a analog signal to a digital signal, we need to go through several processes. One of the process is sampling, right. We need to convert this analog signal, and the data point which we will be converting, we have to first sample them, right. Sample means this T0, T1, T2, T3, in between data we will neglect. So, the data is first sample at time T0, then at time T1. So, these are all called sampling, and after this sampling, it results in a discrete time analog signal. Now, you can see this waveform, still the amplitude covers all the ranges. So, still it is analog in amplitude, but discrete in time. So, this is the first step of conversion due to sampling. So, sampling of a continuous time analog signal will result in discrete time analog signal. Now, after this discretization, we can quantize them and quantize to a digital value. So, for this purpose generally we use ADC, that is known as analog to digital converter, and to do the opposite we need a DAC, digital to analog converter. So, the job of a DAC is to convert a, suppose your processor, you have an analog signal, you change it to digital you do several computation on process on your digital signal processing element or computer or say microcomputer, and after that you need to again convert it to analog domain, because human being we feel comfortable with analog signals, right. So, to do that digital to analog conversion we may need a DAC. Okay. So, any signal and system, the front end and the back end, we will have this data converter and ADC and DAC. Now, if we talk about this digital signal, this is a binary digital signal. So, B0 2 to the power 0 plus B1 2 to the power 1 and so on. So, it is an example of up to n bit, right, 0 to n minus 1, n bit. Now, this bit you can understand that its weight is the minimum, right. Suppose this bit is B0 is equal to 1, then D is equal to 1 into 2 to the power 0 is equal to 1, plus suppose this B1 is 0, 0 into and so on. So, whichever bit will be 0 on 1, correspondingly we can take the total values, okay, and ultimately we will be coming, suppose this is 1. So, 1 into 2 to the power 2 is equal to 4, and suppose rest the bit are zeros. So, what we arrived 5, clear. Now, this lowest weight, this is having the lowest weight, we will call this bit as the LSB or the least significant bit. Okay. We have to define that which bit is starting bit and which bit is the maximum weight bit, right. This bit will carry the maximum weight. So, this will be called as MSB, most significant bit. Okay. These are terminologies that you will be coming again and again in future also. So, from the name you can understand, sometime we just call this is LSB, this is MSB. Okay. Now, let us come to amplifier. So, as I told, in signal conditioning we have several blocks, right. We may have several requirement. Now, suppose some signal, the transducer is producing an electric signal that is so weak that you cannot process. Okay. So, the first requirement is amplification. Okay. Let us take an example. Suppose for biomedical signals, most of these biomedical signals they are very weak. Weak means amplitude voltage range may be in microvolt or in millivolt. Okay. So, for that purpose we need amplification. Now, if I ask you what should be the qualities of that amplifier, what you expect of that amplifier. I want to amplify a signal, but should that amplification change the nature of this signal? Is it desired? No. So, the magnified signal should look like the exact replica of the original signal, right. So, that is termed as the linearity. Okay. So, this one term you remember, linearity. Linearity means there should be a linear relations between the input and output, so that it is amplified, but all the this it should be a exact replica. It is not that I have amplified it, but the original quality is distorted. If original quality is lost, or suppose it looks like little bit of changed, then we will say that some non-linearity is introduced or distortion is introduced, and that is unwanted. So, first and foremost important property of any amplifier is that it should be linear. Now, let us take an example of an amplifier. What I told, an amplifier should multiply, right, amplify. So, suppose Vi is your input signal and your output signal is V0. Now, Vi you are multiplying with and gain A. Okay. So, can you tell me what kind of equation is this? Y is equal to, that C term is not here. So, you can tell that Y is equal to mx, where m is slope, right, slope or gain. What is the meaning of slope? Y by x, clear. So, if I plot it, how will it look like? Straight line, a vertical straight line, horizontal straight line, or a slanted straight line? And what should be this slope? Tan theta, this is m, right, that is your gain, clear. So, this kind of signal are known as a linear signal, okay, clear. So, this is your m. Now, if you have in this signal, if you have higher power, okay, higher powers of Vi, then this no longer remains as linear signal. Then we will say that some nonlinear distortion is introduced, okay, then linearity will be lost. If this equation is modified, suppose this V0 is equal to AVI plus BVI square plus CVI cube, then higher powers are introduced, right, and this straight line nature will be lost. And now the Vi and V0 won't be a exact replica, their shape will be changed, right. So, we will be saying that some distortion is introduced. So, this is our voltage gain, and if we take it in decibel, it will be 20 log, right, 20 log amplitude, and this is the waveform that I just drawn, and this is our AV, this slope is AV gain. Now, we can also have an power gain, right. So, what is my power gain? Load power, this is my load, right, and this is my source, okay. So, what is my voltage gain? You already understand that it is providing a gain, output voltage is higher than input voltage. Does it necessarily tell that power will be also you will be having gain? If a amplifier is providing more voltage, is it necessary that it will also provide you more power? May not be, right, this requirement may be else, or we will come about power efficiency. If a voltage is providing you amplification, does it mean that its efficiency will be also higher? May not be, right, because some power will be wasted as heat, right, heat dissipations. Okay, I will come to this later. So, if we talk about the power gain, this is load power PL and the input power PI. So, what is load power? The power delivered to the load, output voltage is V0, output current I0, multiply them. Input power, input voltage is Vi, and suppose input is providing a current of II, multiply them, okay, and take their ratio, this is your power gain. Similarly, we can also calculate current gain. What is current gain? Output current is I0, input current is II, and their ratio. So, if we multiply this voltage gain with this current gain, we will get back our power gain. Okay. So, generally this voltage gain and current gain, they are 20 log, right. In power we have 10 log, because already V square or I square term is already included. So, we make it 10 log power. Okay. So, if you think about power, if you want to convert power in log scale in dB, it will be 10 log, but in voltage and amplitude it will be 20 log. Now, I was talking about the efficiency. Okay. So, any amplifier or active amplifier, generally we draw like this, right, we draw like op amp, something like this, right. But some other two pins we generally we do not draw. Can you tell me what are those two pins? This is input pins, this is output pin. Any other pin is required for this amplifier to work as an amplifier? Supply voltage. So, generally we will be having two supply voltage pin. One is, suppose we can have dual supply, means plus minus VDD, or we can have a single supply, that is VDD and ground. Clear? So, many of the 741 op-amp series you will be seeing that they are used in dual supplies, that means say plus 12 volt and minus 12 volt. Okay, that will be specified in the data sheet of this particular amplifier, that how much voltage is required. Clear? So, if I have a dual supply, both of these will carry some current, right? To make this operational, this amplifier operational, some internal current should obviously flow, right? You know, biasing, DC biasing, and some DC current will flow. So, that DC current will flow through this VDD to internal circuit, and also some current will flow in the negative bias also, right. So, this current is termed as, this voltage is termed as VCC. Okay. So, this terminologies I will come later. Okay. Suppose this is an BJT based amplifier. So, what are the three terminals of BJT? Collector, base, emitter. So, generally this collector is used on the higher side. So, this voltage source is termed as VCC. Okay. So, for BJT the voltage source is termed as VCC, because voltage source is connected to collector. Similarly, for MOS the voltage source is generally connected to drain terminal. So, it is termed as VDD. So, this terminology I will discuss later, quickly I will come to it. So, this voltage source is VCC and the current it is supplying, this is termed as ICC. Similarly, this voltage source is, it is connected to emitter terminal. So, VEE, and it is opposite in nature. So, minus VEE, and the current is IEE. So, now if I want to ask you that what is the total DC power that the power source is supplying, this is right VCC into ICC plus VE into IE, because this is a total power, right. So, this minus sign is not coming, or you can say this IE will be in minus. So, this is a mod actually, because power will be increased, right. Both of them are providing current. So, this is summation of VCC plus VCC into ICC plus VE into IE. This is my total power that this amplifier is providing. Clear? Now, we can calculate the efficiency. What will be the efficiency? Load power by the input. What is my input? AC signal is this one. This is my AC signal, right. These are DC biasing supply voltages, but this AC signal is amplified here, right. So, this is the total equation, P DC plus Pi, this is input side and this is load side. Output power plus some heat will be dissipated, some power will be wasted, because we can never get 100% power efficiency. Okay. So, this is my final efficiency, PL by PDC into 100, and because of this will never reach 100%. This PL by PDC will never be 1. Okay. Normal class A type it is less than 25%, class B 78%, and so we will be discussing about this later. Understood? Now, this plot have you seen before? No? Saturation, okay, good. Now, I told you about y is equal to mx, right? Can you identify that in this plot? This one, right? So, this is my range where it is y is equal to mx. Okay? So, what is the meaning? If my input voltage stays within this limit, my input output relationship is linear. Agree? If from this point A to this point B, this equation is satisfied, and what I told you that for any amplifier the most important property is linearity. Okay. So, up to this equation my amplifier is behaving like a linear one. So, it will amplify as well as the replica will be exactly same, but after this what I am seeing that it is flat. That means input voltage is increasing, but output voltage is not increasing. So, are they following linear relationship? So, if my input voltage it crosses this range and get into this domain, the moment it will cross this, my input is increasing, output flat, constant, saturated. Where it will be go and get saturated? Let us get back to previous waveform. I have an sinusoidal signal, I have amplified it to something. Now, tell me what should be this maximum value of this range, how much this voltage can go, what will be the limiting value? Who will limit that? Supply voltages. What is the maximum voltage you can have? Plus VCC. You are giving a voltage of 10 volt, can it go to 12 volt? No, not possible. So, it will be limited on the positive side by the positive supply voltage, it will be limited by the negative supply voltage. If this negative supply voltage is a ground, it should be 0. If this is a minus 10 volt, it should be minus 10 volt. Clear? So, this should be limited by the positive supply voltage and this should be limited by the negative supply voltage. Clear? So, in between if I have any sine wave like this, you see it is still within the range, it is still within this range. So, output will be also within the range, but amplified. The moment it will cross this, what do you think? This portion will be clipped, right, because it cannot go above VCC and the linear range is crossed by the input signal. So, it will be also like this flat, you see here this is flat. Why? Because for this is corresponding to 2, corresponding to 1 it is okay, right. Why? Because 1 is within the linear range. Okay. So, this kind of, this is what is this? V0, what is this? Vi. So, this is V0 versus Vi. Okay. So, any plot like this V0 versus output versus input is known as transfer characteristics. This is the transfer function. V0 by Vs is my transfer characteristics, or you can say output input characteristics. Another terminology is output input characteristics. Okay. Another terminology is transfer characteristics. Okay. So, if I ask you to plot the output with time, this is V0 versus t, and if I ask you to draw the transfer characteristics, that is V0 versus Vi. Okay. What is the difference? V0 versus t, it is a time signal. So, that is a transient analysis, transient or time analysis. And here what is the difference? It is a DC characteristic, this is a one DC voltage is changing, right, from 0 to VDD or VCC. So, this is a DC characteristics. Okay. Do not worry, we will discuss about this later. So, you just understand that if this is a V0 versus T, this is a timing, and if this is a V0 versus Vi, this is a transfer, right, input output transfer characteristics. So, is this clear? So, which new terminology you understood today? Saturation. What is the literary meaning of saturation? That it is saturated, means it cannot go more, right. Suppose a chemical, you are making a mixture of water and sugar, and after a time if it is saturated, you cannot make it more sweet, right. You will add more sugar and you will see that it is not getting dissolved, it is lying under the base, right. Why? Because the capacity of absorbing is reached to a saturation level, right. In case of rain or precipitation, you heard this term saturated, the air is saturated, right. So, same thing here, this capacity to go beyond is not possible, because it has reached it. Suppose your voltage is, input voltage is 1 volt and you have a amplification of 12, right. So, 1 into 12 is equal to 12 volt, you are supposed to get 12 volt, but your DC supply voltage is 10 volt. So, you will not able to get 12 volt, it will go and get saturated at 10 volt, clear. So, this concept we will again come and discuss in when we will be discussing BJT. Now, about terminologies. Okay. So, you carefully look this signal and you can see this total current IC, suppose collector current, this total current IC, it has a this component is what? DC component. On top of that you have an AC component. So, this is the total current or the instantaneous current, it has two component, right. One is DC part, another is AC part. Now, you see this DC part, their notation is something different, total current their notation is something different, and AC part their notation is something different. Can you understand? Can you follow? So, this notation we will be following, clear. So, total instantaneous quantities are denoted by a lowercase symbol with uppercase subscript. For example, small I, capital C, IC, total current. So, this subscript is capital, that means total current. This is not about the AC current, this is not about the small current, this is about the from 0 to the actual value. Okay, this is the notation. If we talk about the DC current, what you can see? Capital and subscript is also capital, clear. And if we talk about the AC current, what you can understand? Small, subscript is also small. Okay. So, please remember this notation and we will be following the same convention throughout. So, these are different, this is the instantaneous quantities, this is the direct current quantities, uppercase symbol with uppercase subscript, incremental lowercase symbol with lowercase subscript, and this is another important, I was talking about VCC, VDD, no? So, this define about them. Okay. So, this is a double letter uppercase subscript, suppose voltage source V capital, C, so we will use double CC, VCC, voltage connected to the drain terminal VD, make it double VDD, right, current ICC. Why? Because you can understand this is a notation which is related to the power supply. Okay. Because you may have a drain current IC or you may have a power supply current. IC is a current flowing through the collector terminal, right. IC is the current flowing through the collector terminal. right, but how to differentiate current flowing from the voltage source. So, we use a notation that ICC. Have you seen this before? Small signal analysis. Now, this is an amplifier, general amplifier. So, how it is behaving like an amplifier? What is V0? Output voltage, right. What is input voltage here? Vi, and this is written as AV0 into Vi. So, what is the gain here? This is my gain, right? Right? And if it is an amplifier, what is our aim? This V0 should be this, just like I told you a voltage source. Our aim is to transmit all the voltage to the load. So, similarly here also this ideally should be equal to 0. Why? Then if this is happening, then this V0 will be maximum, right, no drop here. Getting my point? So, if that happens, then whatever the load, this voltage and this voltage will be equal, I will get the maximum voltage possible. So, again some relationship is coming, right. Okay, let us come to an op amp. You have studied op amp, right. Can you tell me the ideal characteristics of an op amp? Voltage gain AV infinite, input impedance Ri infinite, output impedance R0. Can you understand now why it is 0? So, this symbol is nothing but an op amp symbol, voltage amplifier. Okay. Now, what should be this Ri ideally? Now, let us add one voltage source here. What I told you, the internal impedance of a voltage source should be ideally 0, right. So, that this Vs totally comes to this Vi, Vi is equal to Vs. So, now you can see there is a relationship between Rs and Ri. Why? What is that relationship? I told you that Rs should be much smaller than load resistance, that time I termed it as a load, right. So, that this maximum voltage can get into here. So, to satisfy this, my input impedance requirement is infinite, matching with my logic, clear. So, in op amp you have studied that voltage gain is infinite. So, that is my AV0, we want as high as possible. Okay. Input impedance should be infinite. Now, this what is the meaning of infinite? It should be much larger, this Ri should be much larger than Rs, clear. That is why this condition, how much large, that depends on our accuracy requirement. Similarly, this R0, that should be much less than RL, and that ideally we are terming this as 0, ideally we are terming this as infinite, clear. So, can you tell me this relationship? Vi is equal to, in terms of Vs, potential divider, right. This drop I into R by what is? You know how to do that? I into R, right. What is I? Vs by total resistance. You multiply that with Ri. So, that will be equal to Vs into Ri by Ri plus Rs. Okay. So, this is just I term this as a potential divider. So, the output voltage is the resistance to ground divided by total resistance into supply voltage. Clear? So, this is nothing but a KVL, right? You do the KVL, you will get it. Okay. So, similarly, can you tell me what is V 0? This V 0 with respect to this. Can you tell me what is this symbol? This is dependent source, right? Why dependent? This voltage depends on which voltage? This voltage. If this voltage varies, this gain will also vary. Is this voltage dependent? This is a fixed voltage, constant voltage. Okay, so these are symbol terminologies. So, you see this is a constant voltage, I use this symbol. This voltage I use a different notation because this gain multiplied with this. So, this output voltage depends on something. What is that something? Which is related to the input side. So, your output voltage depends on the input side, input, right. In op amp you remember, inverting amplifier, output depends on input into something. V 0 is equal to V I into minus R 2 by R 1. Okay. So, that output is a function of input, that is why this is a dependent source. Okay. So, similarly, you can calculate this, right. V 0 is equal to what? All right. And you again have a relationship between this R 0 and R L, and you know how to calculate that. From this relationship actually what is required, those relationship will come up. For example, if you want V I to be as close to V S, what you can do? You can make this equal to 0, it will become 1, right. If you want to make this as high as possible, what you will be doing? Now, this is V 0 with respect to V I. So, this is my A V voltage gain, V 0 with respect to V I, A V. But if you want to get V 0 with respect to V S, another term will come. You have to represent this V I, replace this by this equation, right. Only mathematics, other than nothing is there. So, another terminology will get added, agree. In ideal situation, this R I by R I plus R S is equal to into what? Ideal case R S is equal to 0. So, this will come as close to R I by R I 1. So, this is also close to that if condition, if this is 0, right. But suppose this is not 0, this is 5 ohm, 10 ohm, then what will happen? Will it change very much? Very small it will change. Now, can you tell me what is this? This is a single stage amplifier or this is a multi stage amplifier. The previous you see, how many stages there? Only one stage. Okay. This is my, this portion is my amplifier, this portion is my source, this portion is my load. Okay, let me just tell you another term. Have you heard this term loading effect? Suppose this is this supposed to behave as an amplifier, right. Now, if this relationship of R 0 and R L is not satisfied, then what will happen? This output voltage will not be as close to this what it is supposed to do, right. If this R L, suppose this R L and R 0 are close, same value, then now still if this output V 0 will be A V 0 into V I? No, right. If they are of same value, it will be potential divider, this voltage will be divided by 2, I just did it, right. So, in that case what we will see, what we will term as loading effect. The output voltage is not able to provide the gain because these constraints are not met. Do not worry, I will discuss this again later. So, if you do not understand or are confused, do not worry, just you just remember this term loading effect. What is the meaning of that? I will come again and again. Okay. So, this is a very important concept. You can understand from this slide, you understand what should be my source voltage resistance, what should be my internal resistance of an amplifier, what should be my output resistance of an amplifier, what should be my load resistance of an amplifier. So many constraints now you understand from this plot or this building block or this symbol. So, this is a, you can understand, this is a 3-stage amplifier, that means as if this is your final output, this is your final input. 3 amplifiers are added one after another, this is called cascaded, right. One stage, there is another stage. So, what generally what we do, why do we do this? What do you think that why you are cascading 3 stage? To get more gain, right, to get more, otherwise why would one do that? You are not satisfied with a single gain, then what you did? You multiplied with another, still you are not satisfied, what you desired is not there, you multiply it with another stage. So, it is like M1, M2, M3. Okay. And if I ask you what should be the input impedance, ideal op amp input impedance? Infinite. What should be my ideal output impedance, means which stage? 3rd stage. Does it require this in between? No, not necessary. So, this should be 0. So, you see that internal voltage source resistance is 100 kilo ohm. What do you think, it is small value or large value? Large value. Does it satisfy my internal voltage source should be 0 resistance? Is it satisfying? No. Then what is the other constant? That the load resistance should be much higher than that, so that we can neglect it, right. So, what is the load resistance for this source? 1 meg ohm. So, now it is relatively higher. So, first condition is, you can say more or less okay, that 100 k is much less than 1 meg, something like that. Otherwise, what will happen? I will not get exactly Vs at the Vi, right, some loss will be there, that is the loading effect. Clear? Suppose you are not getting, you want a voltage source with 0 resistance, but you get a poor voltage source, it is having a high resistance, well, you have to do with that. Now, what is the gain of this first stage? 10 Vi. So, what is the gain? 10. What is the gain of the second stage? 100. You are not satisfied with 10. So, you made it second stage, you made it 100. Now, you see what is the desired output resistance for the first stage? Should be 0, right. So, it is 1 kilo ohm. Okay. To make it 0, this relationship, this is much higher than that, 100 k. Okay. So, for this the output resistance 1 k, this is 10 k. Now, here you see it is, its gain is 1. Output stage, I have already get the desired gain of 1000, 10 into 100, 1000. So, gain is achieved. Now, why the required third stage? To match the output impedance requirement. You see here output impedance is only 10 ohm. So, that it is relatively less, this is my load is 100 ohm. So, I have to design a stage whose output impedance is much less than 100 ohm, but if I stop here, what is my output impedance? 1 k, which is larger than this. So, I cannot transfer my output voltage amplification to the load, clear. So, to match the loading criteria, what was the criteria? That Ri should be much greater than Rs, remember op amp infinite input impedance, and R0 should be much less than RL. So, always remember these two, then you will be having no confusion. Okay. So, we will stop here today and we will continue our discussion from this onwards. Okay, thank you.